Let's get into some trouble. Transformations. A transformation is a change in an object's location, size, shape, or direction. These changes can be categorized by what kind of change takes place. For instance, a reflection flips an object, thereby changing its direction, or what we'll refer to as orientation. We can move an object's location by translating it or sliding it. And of course, if you spin or rotate an object, you'll get a noticeable change in the object because these are rigid motions or isometries, and they preserve size and shape, so they are congruence transformations. Now, if we change an object's size while still preserving its shape, we get this similarity transformation called a dilation. A dilation is the enlarging or shrinking of a mathematical element using a specific scale factor. Dilation changes the position and size of a figure, but not the shape. Since angle measures are preserved, so is its shape. Thus we say similar figures are proportional in size. That is to say, a proportion can be made to establish a correspondence between the sides of similar figures. When a figure has been transformed, it is natural to refer to the result as its image, like a mirror image. And the object before the transformation is usually referred to as the pre-image. A non-proportional size change would be something like a stretch. A little trivia question. Name this Transformer and his sidekick from the original cartoon The Transformers. Leave your answers in the comments section below. Focusing in on reflections. Out of all the transformations discussed so far, reflections are the only one that change an object's orientation, or its directionality. Left and right-handedness gets exchanged or flipped. When we reflect geometric objects living on a plane in 2 dimensions through a line, the image is an object that is congruent, again making the line reflection a line of symmetry, which by definition produces a congruent figure, and the motion observed in this reflection is categorized as a rigid motion. Objects reflected exhibit an equidistance from the line of reflection. The trade-off is a disagreement on the perspective notions of left or right. But things get very interesting when we consider what it's like to reflect an object through a circle. Since a circle is a closed object, it has an interior and an exterior, like 2 sides of a mirror. Reflections through a circle break symmetry of congruence but preserve the character of similarity. And so we get some unexpected but beautiful reflections. And because they're not exactly reflections, we instead call them inversions. Let's take a peek at what it's like to reflect a few objects through a circle. We will start with a point P and its image point P' in red. Observe what happens to the image point P' as I move the point P around the plane. As I move away from the circle of inversion, the image P' approaches the center of inversion. As P is brought back to the circle, its image acts as a reflection would, closing the distance between it and the mirror. But this is a funhouse mirror, and things are about to get a little funny. One key observation one can see is that any point interior to the circle gets mapped to the exterior, and vice versa. Just as reflections exchange left and right-handedness, so does this type of reflection, but with a single point it's virtually impossible to tell what's going on. So we'll need to explore a few more geometric objects. But one can see as we bring the image point on top of the pre-image point, all points on the circle seem to be fixed. So next we consider a line exterior to the circle. We see here that it inverts to a circle interior to the circle of inversion and passes through the center O. Can you think about why this might happen? What happens as we move the line away from that funhouse mirror is that we notice the circle begin to shrink in size. A dilation takes place. Bringing the line back to the inversion mirror, we watch as the image circle expands in size, still attached to the center. As the image and pre-image line come to meet at the circle, on the circle of inversion, we find, just as we would in a regular reflection, that our objects are tangent to each other. If a line and a circle, its image, intersect, the most they can do this at is at 2 points of intersection. Thus, those points would have to remain on the circle of inversion and remain fixed. Observe that when the pre-image line passes through the center of inversion, that the line is mapped onto itself, whereby only the points intersecting the circle of inversion are fixed. And then, when the exact moment of the line passing through its image circle's center, the circles become orthogonal. Because I can't help myself, I want to look at a few more examples. So here's a pre-image circle, which we see maps to a dilated image circle. And just as you might suspect, as we move the circle around, its image reacts in a reflective way, yet scales in size because of the curved perspective at play. Studying circle inversions really calls to attention the role that an observer plays in an actual measurement being made. And as a beautiful property here, when the circle of the center of image and the pre-image coincide, the circles map to themselves congruently. With of course the exception being that the only true fixed points are those that are the ones living on the circle of inversion. As we manipulate the pre-image circle in blue and watch its effect on the image circle in red, we truly get this feeling that the circle of inversion has this lensing effect. Things keep their shape, but they change in size proportionally. Now, of course, as we move the circle away from the center of inversion, the image circle gets closer and closer and closer to the center of that circle. As we move the center of our pre-image circle to the center of the inversion circle, we get a set of concentric circles, where the funhouse mirror is between the two. Now, polygons tend to have a bit more definable characteristics, so we can use them to watch what happens to a hexagon as it transforms under inversion. Now, a hexagon has edges and it has vertices there, and we can see what happens to those edges and vertices as we pass different parts of the hexagon through the circle of inversion. As you would suspect, the straight line segments are being curved in this quote-unquote reflection or inversion. And what we're getting as an image is something quite organic looking. So what happens if we start to move this polygon inside the circle of inversion? Well, as we would suspect, the image and pre-image will intersect on the circle of inversion, and the vertices of the polygon are starting to take shape here. Let's see what happens when we make the polygon sort of concentric. We get this floral looking shape as the image. So you can see there's some very nice and interesting organic looking things that happen under circle inversion. Let's explore the geometry of circle inversion. To see what's going on under inversion, we turn our attention to similar triangles. If we have an interior point A that we wish to project outside the circle of inversion, we create a line passing through it and the center of the circle of inversion O. From there, we will construct a perpendicular line that intersects the circle at point C, meaning that with the radius of inversion r, we construct a line tangent to this circle and perpendicular to this radius. The point A' is the intersection of that tangent line and our horizontal line. Now O, A, and A' are collinear, and A' is called the inverse of A. We will now make use of the fact that we have a set of three similar right triangles to create a formula for inversion. In this diagram, we are comparing the large right triangle to the smaller left interior right triangle. The side with the value of r is the geometric mean of proportionality, and so we get this proportion and the formula for inversion as we cross-multiply. So by cross-multiplication, OA times OA' is equal to r squared. This is our inversion formula, and it'll become very useful in a little while. So now let's return to our diagram. So now one can see that as A gets closer to the center, the construction takes A' further away to infinity. Now with those basics in mind, we're going to derive a formula that relates the radius r of an interior circle to its inverted image circle radius r'. And to do this, we'll have to bring to bear a few geometric theorems. So let's consider our circle of inversion with a radius k. K is the radius of inversion. We have a circle in blue interior to this with a radius of r, and its image circle in yellow with a radius of r'. So first we observe that we can use the lengths along the horizontal to write an expression for 2r and 2r' using a little subtraction here. Next, we can use the inversion formula we just talked about to express what we just wrote in terms of 2r and 2r' in terms of the inversion radius k. So we get OQ is k squared over OQ prime, and OP is k squared over OP prime. Okay, we'll use that in a little bit. We're going to use a little substitution of these two facts together, and that'll give us the ratio of r over r prime, and that gives us, in terms of the radius of inversion k, and the segments OP prime and OQ prime. Now, to go even further to simplify this formula, we're going to summon the Pythagorean theorem as well as the power of a point theorem to express OP prime and a product with OQ prime in terms of OR prime and lowercase r prime, and we get here OC prime squared minus lowercase r prime squared as equal to the product OP prime OQ prime. And pause the video now to put all this together if this is a little too fast for you. But now what we're going to do is bring all of this together into our formula and have a formula for the radius r in terms of its inverted radius r prime and the radius of inversion k. So with this formula here, we can relate the similar objects outside the circle of inversion to the ones inside. Next, we will explore a very unique application of circle inversion. The Pappus chain and the shoemaker's knife. The shoemaker's knife consists of three semicircles, gamma AB, gamma AC, and omega naught, all on the same side of segment AC. And we have semicircles with diameters AB, AC, and BC respectively. Now, tangent to these semicircles, gamma AB and gamma AC, is semicircle omega naught, which has a chain of circles sequentially tangent to each other, as well as the initial two semicircles, filling the space and decreasing in size. From this arrangement, it can be deduced that the circle, omega sub n, will have the height h sub n equal to n times its diameter d sub n, and n is a positive integer. So, problems involving tangential circles are ones where inversion can play a fundamental role. Now let's apply a clever placement for a circle of inversion here. We place the circle of inversion capital omega so that its center, point A, is now at a radius which will pass through omega 3, thereby fixing omega 3, because all points on the center circle of inversion are fixed. When we apply the inversion to the semicircles, gamma AB and gamma AC, what do you think will happen? Note that both of those semicircles pass through the center of inversion. And since they pass through the center of inversion, they will map to straight lines. And since they are tangent to the circle omega 3, they will remain tangent to that circle under inversion. So the inversion maps semicircles to vertical lines, the ones that pass through the origin, that are perpendicular to the line segment AC. And the result of the inversion to the rest of the structure is a chain of congruent circles known as the Pappus chain. Now, here's a quick problem for you to try, and I encourage you to pause the video to figure it out. Find the radius r of the circle in this incomplete shoemaker's problem. Again, pause the video now. Okay, so our approach is going to be to use circle inversion. We're going to let J be the center of inversion and let K here be the measure of the radius here, K equals 6. So the radius of inversion is 6. We can use the inversion formula to calculate a few things, namely R prime. So let's draw our semicircular straight lines, and they will invert exterior to the circle of inversion, since J is at the center. The semicircle B will invert tangent to those two semicircles, and thus be between them, and the Pappus chain of congruent circles will be formed. Here, we just need that second circle to be connected. We find that the measure from KC is going to have to be 3, making the radius r prime equal to 3 halves. And that was using the inversion formula. So the r prime being equal to 3 halves, and we know that the k value is 6, we can also apply the Pythagorean theorem here to find the value of jp prime, well, squared. And here we get 15 over 2 squared plus 3 squared. So putting all of this into our formula for r, we get the radius r to be equal to 6/7. And this was an AMC problem from 2017, problem 16 if I'm not mistaken. Let C be the unit circle in the complex plane, and let Z be a complex number with a radius bigger than 1, making it exterior to the circle of inversion. In polar form, we get Z as r e to the I theta, as well as its conjugate Z bar is equal to r e to the negative I theta. Complex conjugation being a reflection in the real axis. Now, applying the complex inversion of the inversion formula, well, we get Z times Z prime equal to 1. Therefore, the length of the radius of our inverted point must be 1 over r. Now, if we take the reciprocal 1 over Z and 1 over Z prime, 1 over Z bar, its conjugate, we get complex numbers that are exactly the length we're looking for, the inverted points which live inside the circle of inversion. Yet, interestingly enough, 1 over Z is aligned with Z bar, and 1 over Z bar is aligned with Z. We're going to have to pay a little bit more closer attention to what that's going to mean. So, the mapping Z going to 1 over Z bar would be referred to as a geometric inversion because it is aligned with the Z, and its conjugate is known as complex inversion. What we will come to see is that if we want to preserve the direction or orientation, we will need complex inversion instead of geometric inversion. More on that to come. There is a natural way to generalize geometric inversion for an arbitrary circle of inversion K, with radius capital R centered at Q. If we call this inversion capital I sub K of Z, which is equal to Z prime, being the inversion of Z, then what will happen, it will exchange the interior and exterior of circle K, and each point on K will be fixed. Now, this is an example of geometric inversion, and what we're going to need to explore is the effect of orientation change under a reflection in a circle, under circle inversion, in the complex plane. And the way that we're going to do this is we're going to go back to similar triangles. If rho is the distance between points Q and Z, that is, the magnitude of vector QZ, then since Z and Z prime are aligned, oriented in the same direction, we can define Z prime to be the point in the same direction as Z with a magnitude of r squared divided by rho from point Q. We can define a formula for capital I sub K of Z, since the inversion formula would suggest Z prime minus Q multiplied by Z minus Q conjugate is equal to r squared. We can solve for Z prime and get this formula. And we notice that if we let Q equal 0 and capital R equal 1, we recover the inversion in the unit circle centered at the origin in the complex plane, 1 over Z bar. One notices that if we apply a complex conjugation to the inversion, thus giving us a complex inversion, we get our orientation to be restored Conjugation is a reflection, so an inversion plus a conjugation is like a double reflection, giving us the identity. So here we create a series of similar triangles, AQB and B'Q', A'. And what we're doing here is we're recalling that a circle inside the one of inversion passing through the center will map to a straight line. And thus, if we map where the angles are being mapped to in the inversion, we notice that the circle of inversion changes the orientation, the direction in which the angles are being measured. As it happens in reflection, inversions change the orientation or left or right-handedness of the situation. So again, this is where if we take a complex conjugation to the inversion, we will then restore the orientation as a double reflection would in the Euclidean flat plane. Okay, so geometric inversion 1 over z bar is an anti-conformal transformation. It switches the orientation or the directionality. Complex inversion, which corrects for that 1 over z, is conformal, which means that it preserves directionality. More on that to come. Another quite useful fact, or perhaps maybe just an interesting fact, is that inversion preserves orthogonal circles. So two circles, could be the circle of inversion, is orthogonal when they form a 90-degree angle with each other. This feature may not seem all that interesting, but it is this very feature that lends itself to our ability to define derivatives of functions of a complex variable. A conformal map preserves orientation, that is, the magnitude and the sign of angles. Certain transformations in the complex plane are conformal, such as translations, rotations, or dilations. However, inversion in the complex plane is not conformal. We call that anti-conformal. It changes the direction in which angles are measured. A special kind of transformation, which is a combination of the ones we have spoke on, are Mobius transformations of the form AZ plus B over CZ plus D. And these transformations can be decomposed into a sequence of 4 more elementary transformations: a translation, an inversion, a dilation rotation, and another translation. And that combination creates a conformal transformation. So Mobius transformations preserve directionality. They preserve the orientation. Much in the same way we explore the properties of rational functions, Mobius transforms can decompose into a sequence of functions in which we get something conformal as a result. This is the breakdown. And next, I would like to show you an exciting example of one of these types of transforms. Consider the Mobius transform z minus I divided by z plus I. At first glance, this may not seem that extraordinary, but this transformation transforms the upper half plane, sometimes called H, in which all the imaginary parts are positive, into the unit disk. And this transform was used by the work of the artist M.C. Escher in his circle limit works. Here is just one of those works. And it employs hyperbolic geometry. If you like this, I highly recommend checking out his work. And here's a plot of that Mobius transformation. Now, from this, we can get an idea of something called the extended complex plane, and that's through a stereographic projection of the complex plane onto a sphere, which is known as the Riemann sphere. The Riemann sphere fixes infinity. Now, Mobius transformations follow the basic follow rules. They map circles to circles, they're conformal maps, and they obey the symmetry principle. That is, if 2 points are symmetric with respect to a circle, then their images under the Mobius transformation are also symmetric with respect to the image circle. Mobius transformations, it turns out, are very useful in the theory of complex variable functions. But we're not done yet. Mobius transformations have a lot more to give us. You see, Mobius transformations form what we would call a group. That is, they exhibit group properties. If M of z exhibits a group property, we first will require that it is non-singular, that AD minus BC is not equal to 0. Then, it is a bijective map, which means it is both one-to-one and onto. In layman's terms, that is, given any point W in the W plane, there exists uniquely one point Z in the Z plane that is mapped to W. And because it's a bijective map, it is invertible. That means that an inverse exists for it. And here's the inverse. M raised to the negative 1 power is the notation we use for the inverse. And one can check that this is in fact the inverse by composing this with the original Mobius transformation to get the identity. One of the marvelous features of the Mobius transform is that it induces a mapping on the Riemann sphere, and that is a one-to-one correspondence that is established between the Z-sphere and the W-sphere. It allows us to handle points at infinity very nicely. You may also convince yourself that the Mobius transformation evaluated at infinity is A over C, under the limit, and that at negative D over C is equal to infinity, and the inverse property as well. Mobius transformations are an untapped resource of unexpected, beauty, and thus they should be carefully examined for a lot of the things that they're hiding in the complex plane. Another very valuable and interesting feature about Mobius transformations has to do with something called a fixed point. Now, our Mobius transformations exhibit group properties, and one of those things is, what is the action that the group property is defined under? And here, for a Mobius transformation, that group property is composition. If we compose two Mobius transformations, we get another Mobius transformation. And that's true as well for its inverse. So let's take a quick peek at what it looks like under composition of Mobius transformations. So, if we let M1 and M2 be defined here, so that their coefficients have little subscripts 1 and 2, then under composition of M1 and M2, we get the following result, and we see that the following result is a non-singular Mobius transformation transforms into another Mobius transformation, and thus forms a group under composition. So it has some very beautiful properties, not only visually when it is graphed, but algebraically when it is explored as a group. Now, the fixed points of a Mobius transformation. For any function mapping f, a fixed point, let's call it P, is f of p is equal to p. In other words, p is mapped to itself or remains fixed. Now, under an identity map, all or every point is fixed, maps to itself. Now, all the points of a Mobius transformation would be thus the points z equals az plus b over cz plus d, which is really a quadratic equation in disguise. A quadratic equation. Now, you might recall something about the roots of a quadratic equation and how many roots it has. Okay? And so, when it comes to the fixed points of a Mobius transformation, what are the implications of the statement that the equation that we would have to solve to find such fixed points is a quadratic? Well, with the exception to the identity mapping, a Mobius transformation has at most 2 fixed points. That is, if we find that Mobius transformation has more than 2 fixed points, then it must be the identity mapping. So, if the Mobius transformation is normalized, that is, we let AD minus BC equal to 1, then this is the formula that helps us find those 2 fixed points. In terms of A, B, C, and D, the formula might remind you of the quadratic formula. And when we have A plus D equal to plus or minus 2, then these 2 distinct points coalesce into a single point, A minus D over 2C, and we call M of Z parabolic. So this allows us to classify Mobius transformations into one of 4 types: parabolic, hyperbolic, elliptical, or loxodromic. And that might get you thinking about conic sections. There's no mistake there. But what is a loxodromic spiral? Well, that has a lot to do with geodesics on a sphere. That we'll save for another video. For now, Mobius transformations have one more thing up their sleeve. Mobius meets Einstein, relatively speaking. In special relativity, an event is described by a 4-vector, t, x, y, and z, t for time, and x, y, and z for spatial coordinates, giving us a space-time event. Now consider an observer in a rotated coordinate system. We'll call the spatial coordinates x, y, z tilde, and they observe the same point in space. Then they should still agree on the squared distance to that point. However, Einstein showed us that observers in relative motion will measure clocks or time differently. He also showed that they will not agree on the squared distance value between 2 points, one from an observer at rest and the other in motion. And this type of relativistic transformation in measurements experienced by the relative observers is called a Lorentz transformation, and it accounts for the relativistic effects called time dilation and length contraction. And a Lorentz transformation, L, preserves the hyperbolic quantity t squared minus the quantity x squared plus y squared plus z squared. And it turns out that if you set up a one-to-one correspondence between light rays emitted from an event and complex numbers, the complex mappings are those exactly that correspond to Mobius transformations. In other words, every Mobius transformation of a complex number yields a unique Lorentz transformation of spacetime, something Roger Penrose took advantage of in his book, The Road to Reality. Well, that's it for me on transformations, and that's more than meets the eye. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.
Autobots wage their battle to destroy the evil forces of the Decepticons, the Transformers. Robots in disguise, the Transformers.